Okay, so now we're going to talk about power. So power is the time rate of doing work. The average power, so I'll denote that as PAVE or just simply P, is the amount of work done in time divided by that time. So there's also another formula for work. So for example, you apply the force and then the particle is moving with velocity v, so let's say that v is not equal, is undetermined for now. The instantaneous power, the rate at which the force does work, is the scalar product of force and distance, so it will be F dot V. Like work and kinetic energy, which I have discussed in our previous videos, power is a scalar quantity. The SI unit of power is 1 watt. 1 watt equals 1 joule per second. Okay. And there are also other units for power like horsepower. So let's try to grasp how to use the formula with this problem. So how many joules of energy does a 100 watt light bulb use per hour? How fast would a 70 kilogram person have to run to have that amount of kinetic energy? So in our previous slide, the formula for power is work divided by time. Now we're going to solve for W, which is the work. It will give us power times time. Then we will substitute the value, so this will be 100 watts times T in seconds, so 1 hour is equal to 1 hour times 60 minutes and 1 minute is equal to 60 seconds. This is equal to 360,000 joules. So this is the amount of joules of energy that the 100 watt light bulb uses per hour. So let's now solve for the velocity of the 70 kilogram person to match that amount of kinetic energy. So we will use here the work energy theorem, so W divided by delta KE, or just simply 1/2 mv squared. Okay, so W is equal to this one, so 360,000 joules equals 1/2 70 kilograms V naught squared. Now we will just leave the velocity on the right side, so it will be V equals the square root of 2 times 360,000, then divided by the mass, that will be 70. Now your final answer for this one will be computing using a calculator to compute the value. So 2,360,000 divided by 70 equals, oops, sorry, this is, okay, this is 101.14, oops, sorry, So this is around 101.42 meters per second. If we're going to express this in the least amount of significant units, it should be 1.0 times 10 raised to 2 meters per second. Alright. Okay, so let's try to solve a harder problem now. So it says here that a crate on a motorized cart starts from rest and moves with a constant eastward acceleration of a equals 2.80 ms squared. A worker assists the cart by pushing on the crate with a force that is eastward and has magnitude that depends on time according to Ft. So it is in accordance with that function. So this is the function I'm talking about. What is the instantaneous power supplied by this force at t equals 5 seconds? So notice that we have the value for v naught, we also have the value for acceleration, and we also have the value for time. What we don't have is the final velocity, or the vf, to fit with this formula. So p equals fv. So what we're going to do now to solve for v, using the values given in this problem, is to use a kinematic equation. So v equals v naught plus at. This will cancel because it is 0. Now we have here the value of the acceleration, which is 2.80 meters per second squared times 5 seconds. Now our v here will be equal to 14.0 meters per second. Now we are going to solve for the force. So we're going to solve for F. Now F is equal to, of course, this function. Okay, so I'm just going to write it, 5.40 t. Now F, now the time here is 5 as given in this problem. So we're going to multiply 5.40 times 5, and this is equal to 27 newtons. Now we already have the values for the force and the velocity, and we're just going to substitute it into this formula. So it will be 27 newtons times 14 meters per second equals 378 watts. Okay, so now we're going to solve this last problem for our video concerning power. So feel free to pause the video if you want to solve it. So when its 75 kilowatt engine is generating full power, a small single engine airplane with mass 700 kilograms gains altitude at a rate of 2.5 meters per second. What fraction of the engine power is being used to make the airplane climb? The remainder is used to overcome the effects of air resistance and of inefficiencies in the propeller and engine. So in this problem, we are given the mass of the airplane and the velocity. So that gives us an idea that the force for this one will be the weight of the airplane. So I'm just gonna make this first a in pen mode. Then we can now solve for this problem. So P is equal to force times velocity. The force will be the weight of the airplane. So 700 times 9.81 times the velocity, which is 2.5 meters per second. This is now 17,167.5 watts. If you're going to express this in the least amount of significant units, this should be 1.7 times 10 raised to 4 1 2 3 4 watts. Now it asked us to compute for the fraction, so here's how you compute the fraction. So basically you're going to put this in your numerator, so 1.7 times 10 raised to 4 watts over this one. So 75 kilowatts is equal to 75,000 watts. It is also better to use the exact amount, okay, to have better accuracy of your computations. Now when you compute for this one, your answer will be 0.2289, and rounding this to the least amount of significant figures will give you 0.23.